Hello. Um, Welcome to today's video about bioenergetics. So we covered in the previous video some general definitions, introductory remarks about biochemistry. So the next topic we have to deal with is bioenergetics. Let me just, okay, here we go. So a cell is a thermodynamic system, and a general view of any thermodynamic system in this case would be our system in question, whether, so the blue, you can put a cell in there, I mean, as a cell, and the system will have a boundary, and everything outside of that boundary will be the environment. Everything inside that boundary will be the system. Now, depending on what goes in and out of that boundary, the system is either open for matter and energy, whether it can exchange matter and energy with the environment, or not. There are closed systems. I mean, the biggest closed system that we know of is the universe. Okay? But the cell is an open system. It can exchange, all cells, they can exchange both matter and energy in a regulated manner with the environment. So cells are thermodynamically open systems, and because they are, then we can use the basic principle of thermodynamics to describe their properties. So the first person who actually made that connection was Antoine Lavoisier, the father of chemistry, and he measured the heat released by an animal. And you may ask, how could he do that, especially in 250 years ago? Well, those experiments actually were very popular at the time. Remember, this is the time where all the basic theory about steam engines and so on and so forth had been developed. So people were thinking in thermodynamic terms a lot. And the way to do this is to put an animal in some insulated room, and you let it sit there. But let's say at the bottom of at the floor of the room, there is some ice, and you can measure the melting of ice from the animal's action or functions. And from that amount of melted ice, they could go back and actually calculate how much heat is released by an animal or plants. I mean, they did it with every kind of living system. And he essentially found that Antoine Lavoisier and many others, that what you have is really a combustion of some sort. It's like that of a candle burning, pretty much. So that was interesting. So now we can see heat and combustion principles, let's say the same kind of thing that is involved in the steam engines, involved now in living systems, which opens the way to attack it experimentally. So what do organisms do? In some way, metabolism is all about to convert raw materials and energy from the environment, use these reactions to get the stuff you need to make the building blocks of your own cells, not what you get out, not what you get from the outside as food. And of course, thermodynamics is the study of energy and its transformations. So that it all makes sense why we can describe metabolism in thermodynamic terms. What is energy? It's actually very difficult to define it. We call energy anything that has to do with some activity or operation. And there are not too many accurate ways to define energy. The best way, I think, is to describe it in terms of the ability of a system, of a thermodynamic system in the case like a cell, to do work on another physical system. Okay, so you measure work as an output of energy. So now, briefly, the two laws of thermodynamics. The first law is that there is no free lunch. Essentially, all energy is conserved, and you do not get something from nothing. And now we have to also introduce the term of entropy, and that, of course, you've heard many times, and it describes the degree of disorder in any system. And more technically, it's a system's thermal energy per temperature that is unavailable for useful work. So the most significant thing to remember about entropy is that it is a form of energy, but you cannot tap it for anything useful. Okay, it's just inaccessible. Which makes sense that if you have total energy, of some system, and that a component of that will be entropy, then that will take away from the total energy. So the useful energy that you have available to you, if you are a cell to do the things you want, is smaller than the total energy. How much smaller? By the amount of entropy in the system. And in thermodynamics and in metabolism, we care about the changes, the difference in any of these things, whether it's a total energy, useful energy, or entropy. And now we come to the typical equation of the first law of thermodynamics that says basically the differences in total energy are the differences in free energy and difference in entropy. And entropy, because it's a thermal unit based definition, we have the absolute temperature here in Kelvin. So that's all good so far. And because we do care about the useful energy, we care more about the difference in Gibbs free energy, as it's called. That's hence the name G. And changes in free energy is what we're about in biochemistry. G, as I said, came from Gibbs. He was a major contributor in thermodynamics. By the way, historically, he was the first recipient of a PhD of a doctorate in engineering. I believe it was from Yale, but I'm not 100% sure. All right. So, now we have heat, and we're talking about, so we have heat as a factor here in this whole equation, and we're talking about energy, and I've described it as work. How are they related? Well, how do we measure, let's say, in food, okay, the energy content in something that you buy at the grocery store? Usually you find calories. Now, calorie is actually it's a heat unit. So it is the amount of heat that's required to raise the temperature of 1 gram of water from 50 degrees Celsius to 16 degrees Celsius, right? How does that have anything to do with work? Well, how can you raise the heat? You can just put it on the stove, and you have all the fire, burning underneath, and you can raise the temperature of water like that. Or you can take 1 gram of water and imagine an interesting spoon that can actually stir that 1 gram of water and start stirring mechanically. Okay, so no flame or anything like this, just mechanically stir, and eventually you will raise the temperature from 50 degrees Celsius to 16 degrees Celsius. So it's actually the mechanical equivalent of what it takes to raise the temperature, okay, by 1 degree Celsius of 1 gram of water. And that mechanical equivalent is measured in joules. Okay, so you see now the connection between work and heat, and they are related, of course. It takes about 4 joules to get 1 calorie. So back to living system. Who's paying for all this? All right, we are talking about useful energy. Where is it coming from? Well, most of it, the vast majority, okay, the vast majority of organisms, our energy comes from the sun. Unless you are, some bacterium living right next to some thermal vents deep into the ocean with no light there, then you really rely directly or indirectly on the sun. Some of the energy of the sun, a few percentage points, per day, is captured by phototrophs, organisms that can actually do photosynthesis. And it is those guys that are extremely important, okay, at the base of the food chain, let's say, because they use the radiant energy, the solar energy, to generate useful organic compounds, which now they take the form of chemical energy. And it is this kind of food that organisms like ourselves can take and from the phototrophs, eat them and convert them to whatever we want in our own metabolic reactions. Now, so that's the whole cycle here between prototrophs and chemotrophs. And this thing is going on and on and on and on. And of course, there is entropy here. So you have total energy, you have some useful energy here that's happening. So that would be the delta H, when it gets captured by phototrophs, then it becomes delta G in all these reactions. But there is an entropy component here. And in general, this is how they're related. All right. So the second law now says that the entropy of the universe always increases. Okay. So now the universe, however, is an isolated system. As I said, it's pretty much the only very good isolated system we know of. Now, we do all our business here, and entropy will increase, whenever we do our things and go on living. But the increase of entropy does not have to take place in the reacting system itself. So the more we do our metabolism, doesn't mean our own entropy increases. The entropy of the universe increases, but not our own entropy. Okay, that's extremely important. Right? In fact, we're extremely ordered when we are living, super ordered systems, as opposed to the disorder that is generated by the increase in entropy. So all systems tend toward thermodynamic equilibrium. So that's a natural tendency. So if you again take the big picture here, the big box, the universe, the entropy increases. Equilibrium will be when free energy is at the minimum. Basically, all of it is entropy. There is nothing available for other stuff. So living things, we are in steady state, meaning that ideally we don't change much in the differences in energy and composition or chemical composition when we're alive anyway. It doesn't change that much, and that's the way it should be if we want to stay alive. But we are far, far from thermodynamic equilibrium, okay? Very far. So as this gets bigger, in this fundamental equation of the first law that we described, this gets smaller. That's the natural tendency, as we do our reactions, and this is what happens with the universe. And in terms of what is likely to happen or thermodynamically favorable to happen, it is some reaction that satisfies exactly what we described. So that useful energy will get smaller and smaller and smaller, and entropy will get higher and higher and higher. That's the natural tendency. Okay, so any reversible process tends towards a decrease in free energy, because again entropy gets bigger and bigger and bigger. So the delta G for a thermodynamically favorable reversible process will be negative in this case. You're going to have less and less and less free energy. So the farther away you are from equilibrium, okay, the delta G, the actual value of the delta G will tell you how far you are from equilibrium and how likely it is for the reaction to proceed, okay, in thermodynamically favorable terms. It will not tell you, however, if it will proceed and at what rate it may proceed. Let me give an example, and we're going to get back to that example. Imagine you have a stack of wood, and imagine that you want to build a fire. Is it thermodynamically favorable that the wood will be burned? Okay, the answer is yes. Okay, that's once you start burning it, it's a very favorable reaction, and it will happen. It's extremely unlikely that the reverse will happen, meaning that from the ashes you're going to regenerate some load of something. Okay, so that's what we mean. However, just because you have a stack of wood, it doesn't say whether it's going to start burning spontaneously or when that's going to happen and how fast it's going to burn. Okay, I hope that makes sense. So that's the difference. Yes, it is favorable for the reaction to proceed and burn it all the way, as opposed to the opposite scenario. But it doesn't tell you whether that reaction will even ever happen, when it's going to happen, and at what rate. Right. So all it says is just, so the delta G value, all it says is it's how far it is from equilibrium. That's it. And the farther it is from equilibrium, the more thermodynamically favorable it is to have. So for a chemical reaction, the standard free energy change, so here with a little zero, is the value of the difference of the change in free energy in kilocalories per mole, okay, 1,000 calories per mole. Under very specific conditions, when the temperature is, let's say, room temperature, 25 degrees Celsius, at sea level, 1 atmospheric pressure, and this is so these are not so strange the conditions, but the last one is when concentration of each reactant and each product is 1 molar. That's almost never going to happen in real life. But that's the standard free energy change. So it is something to use as a yardstick. For biochemical, this is for the previous definition here, was for any chemical reaction. For biochemical reactions, which happen in water, and they happen also at a specific pH, which is around 7, we have additional conditions for the standard free energy. And by the way, for biochemical reactions, we have a little prime symbol here. So if you see delta G prime, that's a biochemical reaction, which under these conditions, these assumptions have to also be satisfied. So it's happening in water, so the water is an enormous success over anything else. It's constant, 55 molar concentration, let's say, compared to anything else, and the pH is 7. So let's look now at a hypothetical reaction. A and B reacts to give C and D with little a, little b, little c, and little d, indicating the number of molecules of A, B, C, and D that participate in this reaction. And let's imagine that the conditions are not standard. So we don't have everything, for example, being at 1 molar. What's the free energy of that? So of a biochemical reaction. So, and that's extremely important here. So it turns out that the free energy under non-standard condition depends on the molar concentrations of the reactants and products. So for example, if you have a lot more of the products, all this equation says that if you have a lot more of the products compared to the reactants, the reaction is very unlikely to proceed, from left to right as written. It's going to go the other way, from the products go towards the reactants, right? So the other terms we have not seen before. Again, T is the temperature in Kelvin. R is the gas constant, right? And of course, we also include here a term for the standard conditions, whatever, when all the concentrations are at 1 molar. So you plug in all the values for the reactions you have, assume you have measured, the concentration of each of these products and reactants. You can plug them in the equation, and you're going to get the delta G prime value, the change in free energy. So this term in the equation, where you have all the ratio of the concentrations, this of course is the mass action ratio. And again, all it says that the reaction is more likely to be favorable when it goes from high concentrations to lower concentrations, right? So when you're not going to, otherwise the reverse is not going to be thermodynamically favorable. And we have a specific term to indicate the ratio of the concentrations. That's K, of course. And then we can rewrite the equation in a more familiar term. These are that's the non-standard change in free energy. And it is, again, a function of the ratio in concentrations of products and reactants. To simplify even more now, at equilibrium, the reaction will not proceed, which means, so if the reaction that we wrote here is at equilibrium, okay, back here, for example, at equilibrium, this reaction will not proceed. So there is not going to be any free energy change. That's the definition of the total equilibrium, when there is no free energy change. So at that point, the delta G prime goes away, and then we have an actual value for the standard free energy changes that we can measure now. And even though, again, it corresponds to unrealistic 1 molar concentrations of reactants and products, doesn't usually happen in nature, but as unrealistic as it may be, it does provide, again, a yardstick, a useful, we can have our own ruler, and we line up all these various biochemical reactions we care about, and for each one of them we have a delta G prime, other standard conditions, what that is, and that value and sign, again, negative or positive, of that reaction will tell us something. So let's look at some examples. Oops, not much. Okay, here. If we have a fermentation, whether you make bread, let's say, or beer, or something like this, this is how the reaction is described. You start with something rich in glucose, and you produce ethanol and CO2. That's fermentation. And the delta G, the standard energy change for this reaction is a negative sign, 56 kilocalories per mole. Right? So that's a number. We can put an actual number. That's all that it says to it. If you take this glucose and completely oxidize it, whether you burn it, imagine, the equivalent of glucose, you light it up and all that, all the way to CO2, not to ethanol, but to CO2, in the presence of oxygen, you're going to get a much bigger absolute change in delta G, 686 calories, so more than 10 times, okay, compared to what you got with fermentation. So what have you learned from that? It tells you that if you go through complete oxidation of glucose, which, by the way, as we'll find out, and I'm sure you've heard before, it happens in our mitochondria. That's the total reaction that will happen along with glycolysis. Then you can burn all that glucose you get in your food, and this is the total free energy you're going to get out of it, which is enormously more than if you just ferment it. So all you care is about how much energy you get, whether it's just glycolysis and fermentation or glycolysis and full oxidation of glucose into the mitochondria. Obviously, the latter pathway will give you a lot more free energy. So 2 points here. The negative sign shows that that's a thermodynamically favorable reaction. You start with something that has a lot of free energy, and you complete the reactions and gives it away. And the value, so the sign says it's favorable, and the value shows the magnitude, okay, of the change of this thing. So the negative, and the more negative you are, that says it's a lot more favorable to happen. Chemically speaking, it doesn't matter whether you burn glucose biochemically, as I described, or chemically by combustion. Okay? In the example I described earlier, you take a stack of wood and you light a match and you burn it. The actual free energy change will be exactly the same, okay? Assuming again that your wood is made 100% of glucose. So is this how our cells do it? Even though Lavoisier said that the animals are like the candle, the flame on a candle and all that. Actually, no. That would be a pretty bad outcome. If this is how your cells decide to do their chemical reaction, that would be horrible. The reason is that, of course, our cells, we are isothermal systems. Organisms are made of cells, so we and the cells, the individual cells, are isothermal. So the reactions have to happen at normal temperature. I mean, no change in the temperature. Let's say for us is 37 degrees. And you cannot, when you burn wood, you just light a match, you have some heat released, and then everything goes super fast. And the heat from, when you start burning wood starts burning more wood, the flame gets bigger and bigger and bigger, and so on and so forth until everything is up in smoke. You cannot do in biochemical reactions. You cannot use the heat released by one reaction to power the next one and the next one, because you're going to burn yourself to death, right? So the way things work with the wood that I described can be described like this. I mean, you combust a pile of wood. You have to go over some activation barrier. How do you do that? By lighting a match. Okay. And once you go over that, then everything happens extremely fast. All of the free energy is released in one step. Nothing as heat, okay, and nothing is stored. This is not a good outcome if you're a cell and you want to use the free energy you got from your food. In this case, you have a nice sugary meal, carbohydrates. You want to burn them in little baby steps. So each one will have a little bit of an activation energy. So you go over it. So enzymes will help you do that, okay, to go over the hump. And you do them in little baby steps in a series. So you have smaller activation energies. You don't have to have the super powerful match, to start burning your pile of food. And the other, the two key advantages is you don't release a lot of heat as you do it. Okay, very little heat, so you don't burn yourself, number one. And number two, the free energy, you can store it from one step to the next, so you can use it in different ways as opposed to letting all go away as heat. So this is us. This is the inorganic example that I described by burning, let's say, food. The other useful property of delta Z's is that in a sequential chemical reaction, like this, for example, you could imagine that a delta Z, okay, in general, the total delta Z has to be negative for the whole sequence of events. Then the pathway will happen. The whole sequence will happen. If it's positive, it's unfavorable thermodynamically, as I said. But what if you have several steps that are thermodynamically favorable, so negative delta Z, and one or more that are positive? Then are you stuck? No, by coupling them together, because the delta Z's are additive action in the pathway, you can end up with, as long as you end up with an overall negative value, you're okay. It can happen. So you can couple then one favorable reaction, one or more favorable reactions with an unfavorable one, and in the end you have a favorable outcome. So that's another useful property of delta Z's. They are additive. All right. So now I'm going to switch gears just a little bit. And we talked about delta Z's and free energy changes. But the basis of many of the reactions we're going to be talking about is the movement of electrons. Okay. So organisms in general obtain energy from redox reactions, oxidation and reduction reactions. So you move electrons from one molecule to the next, or even within one molecule, but from one atom to another one. So how does that fit with the whole thermodynamic discussion we're dealing with? Let's go through some terminology first. So the molecule that loses electrons is oxidized. The molecule that gains electrons is reduced. So if you get all these electrons, you're going to be reduced. By the way, just going back to this, food in general is rich in electrons. So yeah, with our food, we get electrons, and as you move them on, okay, so our food gets oxidized in the process. In this case, eventually releasing CO2. So you can see some connection already. All right, so how do you write this reaction? Let's assume that something will be reduced, so it starts in an oxidized state. It picks up, let's say, a couple electrons, and then it gets reduced. So, by the way, everything is color-coded here with a black-red, like your battery, in your car, kind of the same way. Try to make it simpler so you can follow. That's going to be a half reaction, and half reactions are by definition or by convention rather, they're written as reductions. So whenever you see some half reaction like this, it will always be depicted as a reduction. You're not going to see it in reverse. So A red minus 2 electrons, A ox. Okay, it's always going to be as a reduction. So there is a standard half cell potential called E. Okay, so the half cell potential under standard condition is the energy now. So now we start seeing energy again of the transferred electrons. Okay. So these electrons have energy. How much energy is defined by their standard E prime value. If that's a negative E value, the agent is reducing, so it will get oxidized itself, so it has a tendency to pass its electrons to something else, and vice versa if it's a positive value. All right, so just to make the point that this is how we go from electrons now to energy, and the way we measure current, let's say, is with volts. So that's the electric potential difference between 2 points. And where does work come into play here? So we're talking about energy, we have to talk about work. It's the amount of work you have to do in moving charge from one point to the other. So that's 1 volt, okay? And you have to move 1 coulomb. It's the amount of charge carried by a current of 1 amp per second. So here we have amps, we have volts, we have joules, which is work, and we have coulombs, which is the unit of charge. As it turns out, to move 1 mole of charge, okay, across a potential of 1 volt, just 1 volt, you need an enormous amount of energy, okay? 96,500 joules of energy. But what is an amp? We haven't talked what is an amp. You don't need to know. It's not going to be in the exam. It's just kind of curiosity. Everything is very well defined. We have defined joules, we have defined volts, but we have not seen amps here. And amp, as it turns out, amp until recently, maybe 4 or 5 years ago, it had no rational definition. The definition was just extremely convoluted. You have to imagine all these infinitely long wires, 1 meter apart, and depending on how much they attract each other when electrons were moving in them, you could define some force, okay? And from the force you go to all these other energies, all these other units I talked about. So it's very convoluted and very difficult. It was very difficult to define. Again, the point here is that everything does come down to force and joules and work that we have talked about. And it's kind of a little factoid here. Finally, we have some rational definition. And because people could actually follow individual electrons, and they can define them now by a new unit that will replace and will have a better definition of the amp by being able to follow individual electrons. We could not do this before, but now with some microchips, physicists have been able to track individual electrons with them. All right, on some semiconductor chips. Anyway, that's a factoid. Let's get back to our mundane redox reaction. So we described one part of this. We have something that gets reduced. The AOX gets 2 electrons and gave you the A red. That was the half reaction we described earlier. Where did you get the electrons from? Well, it got them from another compound, B, which had the electrons, so it was reduced. And when it gave them to A, it became oxidized. So a complete redox reaction is never a half cell. It's always something gets reduced, something gets oxidized, and you have to couple them together. So the tendency of the transferred electrons to go, from one molecule to the other is given by the difference in the electric potential, which is the delta E. Here we come with deltas again. So how do you calculate the delta E of a reaction like this one that you see here? Well, you subtract. So you go to the half cells. Sorry, let's go back. You go to the half cells, and there are actually tables that you can find the standard, anyway, half cell potentials, or you can actually measure them, as I'll show you in a minute. So, but under, let's say, standard conditions, there are actual values. And then what you do, and that's very important, we're going to do this many times in class, to calculate the delta E, you subtract from whatever gets reduced as a reduction. In this case, would be this half cell, the first one we discussed. AOX gives you A red. So you get a number and you put it right there. And from that number, you subtract the E value for the B reaction as a reduction, the half cell, okay? If you don't reverse anything, okay, that's a subtraction. And here both of these half cells, you get the E values from written as reductions. So you subtract those, and that will be the delta E. And again, you can literally get actual voltage here, okay, of this redox reactions. If you can imagine, you put them in different containers, you have a voltmeter in the middle, and you see the flow. You can actually measure the actual flow of electrons. The point here is that much like the battery in the batteries that you are used to, you can have a little, I don't know if you were kids, when you were kids, you had a battery and you can hook up a little cable, and you can put a little propeller and you can see it turning and things like this. You can really couple the flow of electrons, which comes down to basic fundamental chemical properties, to some electromotive force, that's the flow of electrons, and then do work. You have some kind of motor. Let's say I mentioned the little propeller there, and it will do work. And this is how these reactions work, okay? So you can see how redox reactions, let's say, where do the electrons come from? They come from our food when we eat. They are rich in electrons, and you can use them to do biochemical work. So this is our scheme that we saw earlier. We have the total energy, we have the useful energy, and of course, the more of that stuff, whenever that stuff is going on, the more entropy it produces. But the proper real-world view is to replace all that stuff with just redox reactions there. We are little batteries, as you will see, and that's going to be a major theme in the class. You will see that the way cells get their energy is to literally charge their batteries. They have real, actual batteries, and they, mitochondria in eukaryotic cells. In bacteria is a little different, but still the same principle. And as long as you can put some motor, hook them up in those batteries, then you can actually make stuff happen. So the standard half cell is the hydrogen. Okay, so when you make you get 2 protons and 2 electrons to give you hydrogen. By convention, that's going to be 0. So at pH 0, however, and that gets now it gives us a reference point for everything else. And the energy of electrons, the points that the more negative they value, the higher the energy. Okay. At pH 0, that would be that would be 0 volt by definition. But at pH 7, which is a physiological condition for living systems, the value for the hydrogen half cell is actually minus 0.42 volts. So it's actually quite negative. So that would maybe put it right there. So it has quite a bit of energy. So delta E prime, just like the delta Z, reflects the tendency of the reaction to proceed under standard conditions. So it's very similar to delta Z prime. Again, doesn't tell you whether the reaction is going to happen and when it's going to happen or how fast it's going to go, but it tells you the general tendency, thermodynamically speaking. Okay. And it's under the exact same conditions as a delta Z prime. So it's a useful yardstick. Any species that accepts electron from normal hydrogen, electron is a half cell with a positive redox potential. And any species donating to the hydrogen electron has a negative redox potential. How are the delta E and delta Z related? This is the equation. We replaced a lot of stuff that was here on the delta Z definition with delta E. We have not seen these 2 terms. F is the Faraday constant. So it's a constant, and N is the number of electrons. We'll talk about the minus sign in a minute. Okay. So, F, of course, for Faraday, who was the giant of electrochemistry and electromagnetic theory. Now, in non-standard conditions, so this is under standard condition. Okay, so 0, the prime 0 here. Now, if they are not standard condition, so not 1 molar concentrations, let's say, and so on and so forth, we here see again concentration of reductant and oxidant, okay, coming into play. That form of the equation is the Nernst equation. And if you look at it, it looks extremely similar, right? So you have this is the standard conditions, that's the delta E value here, and we have concentrations of the redox partners, and that will give you the non-standard change in the electric potential. Likewise, as we have seen for delta Z, that's the mass action here with concentration of reactants and products. So for the half cell, we can write even a modified Nernst equation. Okay, just we deal with only one of the participants there. And what's important to remember, and I think you can forget the previous stuff, but in general terms, the previous equations I mentioned, but what's really important to remember, when we discussed delta Z, something was thermodynamically favorable. It gave us the tendency of the reaction to happen if the sign was negative. However, the delta Z and delta E signs are opposite. Okay, that explains this point here. So for something to be favorable, the delta E has to be positive. Okay? Then the negative sign would be maintained, and delta Z would be maintained, and delta Z would be negative. So if I ask you now in practical terms to tell me if a redox reaction is favorable, the delta E that you will calculate, if it's positive, then it is favorable. Okay. If I ask you to tell me if some other reaction, but based on the delta Z now difference, if that reaction is favorable or not, make sure that delta Z is negative in that case. Okay, so opposite sign. This reiterates what I just told you here. Redox reactions, oh, by the way, so this is my favorite example here. What's favorable or not, so as long as you couple a reduction oxidation, you get a delta E. That's positive, that's a favorable reaction. How do you know? You have to know the E values for the half reactions. And if you, in a sense, you're making a battery, okay? And you want to make it so that you couple oxidants and reductants in a way that you have a flow of electrons. And if you do, then you're going to have a positive delta E, and that is going to be a battery. So if for the fans of Breaking Bad, like myself, this is what the protagonist of the show had to do at some point when they were out in the desert doing their bad business, and their car battery died. So he literally made a battery from scratch because he knew the different metals he had, how to put them and couple them together so he can get a positive delta E. Right? So he was super smart, knew all the delta E values for the various metals. We don't even have to worry about this because there is really, there are very few things that we're dealing with, very few reactions in biochemistry. Carbon that's stuck to oxygen in this case, various states of oxygen. So if it's a carboxylic acid, if it's a keto group here, an aldehyde or an alcohol, or fully reduced, all this will have the highest number. A hydrocarbon essentially will have the highest number of electrons. That's going to be the easiest to. That's going to be ideally the food we're going to take. It's going to be more and more reduced, kind of like the gasoline we put in our cars. It's hydrocarbons. It's in this state, and then we burn it. We increase the oxidation state as we burn it. Kind of the same thing happens in our cells. We start with something reduced, maybe not as reduced as this, but hopefully something like this, and we drive it to more oxidative states, and in the process we get the electrons out. Those are favorable reactions going this way, right? And we can capture some of this free energy. That's another way to depict this. This is you can line up, the half reactions here. You go from a carboxyl group to a carbonyl group, carbonyl to hydroxycarbon. That's the alcohol that I mentioned earlier, and the alcohol then even more. You can take the electrons from that and make a hydrocarbon. Okay, and the E values, how they are related, are shown on this for the half reactions, are shown on this scale. And if you have and we're going to work with this scheme many times. So the idea is if you have one reaction that looks like this and another reaction that looks any one of those two, if you couple them together, it's going to be favorable or not. So we have to learn how to do the delta E calculations, all right? So, but we'll get to that example later in the class. Well, maybe we can do one now. All right. So let's say you have you want to couple the reduction of a carboxyl group to a carbonyl group, okay? And so that's what's going to get, it's going to give you the more reduced form here, and who's going to donate the electrons? One of these reactions, right? So how do you calculate the delta E? Well, you start with something that's going to get reduced. So if that's what you want, okay, the delta E here will be, so the E for that half reaction will be, let's say, minus 500. Okay, minus 500 millivolts minus one of those two. Let's pick the green one here. Minus 100. Okay, so we start with minus 500 minus 100. Minus is plus 100. So minus 500 plus 100, that will give you a final delta E of minus 400. Is it favorable or not? The answer is it's unfavorable, the way I described. So if you have a reduction of a carboxyl group to a carbonyl group, and you couple this with an oxidation of a hydroxycarbon to a carbonyl carbon, that is an unfavorable reaction because the delta E will be, a negative value. So that's one little example, and we're going to do a lot more. So don't worry too much if you didn't get it right now. All right, so almost to the end. So again, chemotrophs, what they do, they use high energy electrons from food. So this is us, a chemotroph. We take organic compounds rich in electrons, and usually we pass them on to an acceptor like oxygen when we breathe in and out, and we release free energy, and then we can use it to do our business. Prototrophs, what they do is they use the energy of light to raise electrons from low to high energy. And then they transfer them to an internal acceptor, and that's how they release free energy so they can do their business. Okay. In the process, when they do their business, they generate food for us. So hopefully that convinced you that that's really the real view of energy and matter in the biosphere. And by the way, it hasn't escaped. There are even startups that are trying to do this, to implant us with photosynthetic pieces that we can actually harvest energy from the sun. Right? And so that's the general idea. That's all I had to say about bioenergetics. This concludes this video. And the next one, we're going to go on with fundamental energy bonds in the cell. So thank you, and I will see you next time.